You know what separates an average developer from a grade one? It's not how many languages you know, it's how you design things. In every interview, there is that one question: how do you design this? And that's where most people panic. But here's the truth: almost every real world problem you will face as an engineer boils down to a handful of design patterns. And once you understand why they exist, you start seeing them everywhere. In this video, I've compiled the 7 most popular and most asked low-level design patterns for you. The one every interviewer secretly hopes you understand. We will talk about how the Singleton quietly runs the show behind the scenes, how the factory helps you build without chaos, how strategy and adapter makes your code smarter and more flexible, how observer keeps things in sync, how builders simplifies complexity, and how state brings life to your objects. These aren't just theory, they are stories of how great systems are built. So grab a coffee, sit back, and let's decode the patterns that power every smart design you have ever seen. So let's get started. You don't even knew this was a singleton pattern. How did you even become a software engineer? One of my seniors was holding my teammate, and I was so scared because I knew the next one was mine. I hope this story terrifies you into learning singleton pattern. So let's try to understand what exactly is a singleton pattern. I don't like definitions. So if I have to tell you or explain this by an analogy, I would say if your life is an application, your mom and dad follows the singleton pattern. Unique, irreplaceable, and always there for you. If you didn't get what I mean, you will after this video. So let's try to understand this with an example. Imagine an airport bustling with planes taking off, landing, and taxiing on the runway. How does all this happen so smoothly? The answer is central tower. At any airport, there is one central tower that coordinates all these movements. Pilot communicate with the tower, and tower ensures that everything happens in an orderly manner. What if there were multiple central towers at any given airport? There would be conflicting instructions. For example, Tower 1 may instruct a plane 1 to go on a lane 1. The other tower may not know about this, and that may instruct another plane to go on the same lane. This will result in a complete disaster. So that's why having a single central tower is the best approach to ensure smooth operations. And that's what exactly a singleton pattern. Now let's try to understand this through code. Let's imagine you're creating a system where we can create an instance of the control tower. So what we normally write in code is simply we create a class called control tower. We write the init function or initialization, and we simply bring initializing control tower. Okay. So, as we saw, an airport should have only one control tower. So, we create tower 1 is equal to control tower. But say somewhere in the code, we mistakenly create another instance of the control tower. So, what we want is the tower 1 and tower 2 should be the same. It should not create another instance of the control tower because we know that will result in a chaotic situation. So, let's see if this gives us the expected output. So we want to check is if tower 1 is tower 2. Let's run this code and see what we get. So the tower 1 is initialized here, tower 2 is here, and tower 1 is not equal to tower 2. So let's fix this with our singleton pattern. So we don't want to create new instance every time we invoke control tower. So what we can do, we can have a class variable called instance, and we can initialize it to none. And instead of controlling how we initialize the object, now we actually want to control how we create the instance of the object. So we can safely remove the init method and customize the new method. The new is called before the init because init controls the initialization of an instance, but new actually controls how we create an instance. So here we can check if class dot instance is none. If it is none, then and only then we create a new instance. So for this, what we can do, super dot underscore new class. So what this does is it checks if the class instance is none, that means no instance of this object has been previously created. We can simply write the comment check if an instance already exists. If it does not exist, we create the new instance and we simply return this instance. Here we can also write, since the instance is now created, we can have like initializing or control tower. Make sense? So what this should do is, if we are creating the control tower for the first time, it should see that there is no previous instance and it should create a new instance of the control tower. But the next time we create the instance of the control tower, it should return as the existing one. So let's see for an example if this returns true this time, if control tower 1 and 2 are the same. So if we run this code, interesting, it still gives us tower 1 is not equal to tower 2. So what is going wrong here? Let's check our code. Oh, so this return should come here. Now let's try again and boom, we see that the tower 1 is equal to tower 2. And even if we create another instance, say tower 3, this should be equal to the previous instance of the tower. Let's run again. True. So every property or method of this class instances, say tower 1, 2, and 3 would be shared because it's the same. So for example, if we have like another method for the class, say manage flight, and we just give it a flight and simply says managing flight, but we give it a f string. Okay. So, if I write here, power one, log manage flight, and say we give it a name A123, and tower 2 manage flight B456. So, and we run it. So, even we call manage flight on tower 1 and tower 2, it's calling the same method of the same instance because tower 1 and tower 2 are actually the same instance. So we have the centralized way of managing all the flights. So it's not like the tower 1 is a totally different instance which is managing a different flight and tower 2 is managing a different flight. So we now have created singleton pattern that ensures centralized coordination between all the flights on the airport. So I hope you have understood why do we need a singleton pattern and how to implement this in a code. It's very simple. I would like to give you another examples of singleton patterns. So for example, you can imagine we have a database connection. So what if every time we have to write some data into a database, we should not create new connection, or every time we want to read data from a database, we should not create a new connection. So there should be a singleton for the database connection. Every time we require to read or write data from the database, we should be using the same connection. That can save us a lot of bandwidth cost, and that will not overwhelm our database and our application. The same goes for the logging. For example, if we are logging some data to a file or putting logs to a file, every time we log something, we don't want to create a new connection, open a file, write data to a file. We just want to have a singleton for that logging mechanism. So these are some examples of why we need singleton and why not having a singleton can create a real chaos and can be devastating for application. So I hope you now understand the importance of the singleton design pattern.
Let me share a quick story that might sound familiar to you. A few months ago, I was working on a project for a global e-commerce platform. We started with three types of users: buyers, sellers, and admins. Creating objects for these types manually was simple and straightforward, but then more requirements started piling up: guest users, moderators, premium members, and even regional managers. Suddenly, my code base was full of conditions, copy paste logic, and unpredictable bugs. It was like adding patches to a leaky boat. Fix one issue and two more pop up. So that's when my teammate introduced me to the factory design pattern. And let me tell you, it completely changed how I approach the problem. Today, I'll walk you through what it is, why it works, and how you can use it to make your code more flexible, scalable, and more importantly, bug free. So let's get started. So let's try to understand this better through code. Imagine you are building an app for a pizza shop. So you need to create different objects for different pizza types like veggie pizza, pepperoni pizza, and cheese pizza. At first, you might think it's simple. Just create separate classes and create different objects manually. Pretty simple, right? So let's see how that will look in code. So this is how it will look like if we create separate classes for each pizza type, like cheese pizza, and we have a prepare method, same for the pepperoni pizza and a veggie pizza. And in our main code, when we want to create different types of pizza, we instantiate each object separately. To start with, this works totally fine. There is no issue at all. But what happens when we want to add new pizza type or when customer can choose dynamically what pizza he wants? At that point, it gets a little messy. So let's try to understand what I mean by that. So for example, instead of predefining what pizza we want at the compile time, say we get a user input for the pizza type. In this case, it's a pepperoni pizza. Now we want to create pizza based on the user input. What we will do, if input is equals to pepperoni, then return pepperoni pizza. Elif if input equal to veggie, then return veggie pizza. You get what I mean, right? And similarly, elif input e- so we return cheese pizza. Else print no valid pizza. Okay. So there are three main problems. The one is it is tightly coupled. Let me remove this. Here we are calling the pepperoni pizza in our main code. Same the veggie pizza. What if we wanna change the name of the class, or what if we wanna discontinue the veggie pizza? Every time we wanna make some changes, we'll have to edit or modify our main code, which is not a good way to write modular and scalable code. The second one is if we add more pizza types, our if else statements grows and it becomes a complete mess. For three, it's fine, but for example, if our pizza shop grows and we add 10 more pizza types, that will result in a complete disaster to maintain the code and if else conditions and whatnot. The third thing is it's very hard to scale. Adding new pizza means changing code at multiple places. So, for example, here we'll have to create a new class. We'll have to modify the code everywhere we have explicitly calling that class. So you know that it's not the very good approach to write the scalable and maintainable code. So to solve this, we have the factory design pattern. It's some sort of a factory. So we don't have to explicitly say pepperoni pizza or veggie pizza. Imagine it's like you are the pizza shop owner. Every time a customer places an order for a veggie pizza, it will be very hectic for you if you go into the kitchen, prepare the pizza, and serve to that customer table. Instead, what if you hire a chef which knows how to prepare each pizza? All you have to do is take the order from the customers and just tell the chef that prepare me this pizza. And it's the duty of the chef to give you that pizza. So it makes your life very easy. That's exactly what we do in the factory design pattern. So, as the name suggests, we have the factory which takes all the responsibility of creating different objects. You name it, and the factory will manufacture it for you. So, let's try to understand this through code. So, we have the base class pizza, which has this prepare method which will be overridden by the subclasses. And we have different classes for each pizza type. Say, for example, cheese pizza, which extends pizza class, and same with the pepperoni pizza and the veggie pizza. Now we also have the pizza factory. It handles all the conditional logic for us. So, for example, in our main code, we don't have to worry about which class to call. All we have to do is we call the pizza factory and ask it to create the pizza. based on the user input. And it's the duty of the pizza factory to figure out which pizza to create and how to create it. So, for example, here we want a pepperoni pizza. So, all we do is call the pizza factory, call its create pizza method, and give the user input pepperoni. So, let's look at the pizza factory class, what it does. So, we have the static method create pizza, which has the if else statement. So, why this is a good code? So, let's go back for a moment and think of the three problems we had. The one is the tight coupling. So, now in our main code, we do not have any tight coupling to any of our pizza class. All we do is call the pizza factory. So in future, if you wanna discontinue the veggie pizza, all we have to do is edit the pizza factory and remove the veggie pizza class. And that's it. Our main code stays as it is. Or if you wanna rename the classes or modify the classes, it all will be taken care in the pizza factory itself. So we have solved the tight coupling problem. Now let's look at the messy code. So we don't have a real mess in our main or the client code. All we call is a pizza factory, and all the logic or all the conditions for creating pizzas and any customization lies in the pizza factory. So that is a very good approach because we now have a neat and clean code, and that requires very less maintenance because every time we want to change something, we have to modify the pizza factory and not the main code. Let's look at the third one, which is hard to scale. So now with the factory design pattern, our code is now very easy to scale because our main code stay as it is. And every time we want to add new pizza or modify the classes, we do at the pizza factory level and we do not go beyond that. Our main code stays as it is, and that gives us the flexibility to extend the code very easily and customize the code as we want. So now if the user wants to create a pizza, you just call the factory and let it do its thing. Your main code stays clean and focuses on the logic and not how the pizzas are created. So with the factory design pattern, we have centralized the object creation in the pizza factory class. And our main code is decoupled from how the objects are created compared to when we are not using the factory design pattern. So now you have seen how the factory pattern simplifies object creation and makes your code foolproof and future proof as well. Before we go off, I would like to tell you at what scenarios you'd like to use the factory design pattern. For example, like we saw in the pizza shop, suppose you want to create a course website where you have different types of courses. So the factory design pattern can be an ideal choice. Or suppose you have an e-commerce shop where you have different types of products or different types of orders. Let me tell you a story. I was working at this pharmaceutical company where they had different types of orders. One can be the medicine order, one can be the lab test order, one can be consultation order. So all these orders were being created through the factory design pattern. So at times where you feel that there are some similar types of objects with slightly different implementation and logic needs to be created, and in future you might add more of them or more similar types of objects, think of the factory design pattern as your first choice. So I hope you understand how factory design pattern makes your life easy, and I hope you'll use this in your own project. And the next time you see the factory design pattern in your code, don't panic because you know what it is and how to use it. Imagine you are building a stock market app. Your users want real-time updates for dozens of stocks, email alerts for price changes, and SMS notifications when a stock hit a critical value. At first, this seems very manageable. Just update the dashboard and send notifications manually, right? But as your user base grows and more features are added, the code becomes a tangled mess. You're writing the same repetitive logic, bugs are creeping, and scalability is out of the window. So how do you fix this? Enter the Observer Design Pattern, a game-changing solution for managing dynamic real-time updates in your application. In this video, we'll break down how the Observer Design Pattern works, walk through the code step by step, and explore how it keeps your code clean, efficient, and scalable. So let's start with the normal approach. Imagine you're tracking the stock's prices and displaying it on the user's dashboard. So here's a simple implementation in code. So we have a stock class like this where we have its name and price, and we also have the method to set the new price of the stock. And we also have our dashboard class, which looks like this. It is very simple. Just give it a stock to track, and whenever we call update, it split out the name of the stock along with its price. So how do we use this? For example, we want to track an Apple stock. So we create, this is the Apple ticker with the current price of 150. So we call the dashboard with the Apple stock in it, and every time the stock price of the Apple changes, like from 150 to 155, we have to manually update the dashboard to reflect its new price, right? So this works fine if there is only one stock and one type of update, right? But what happens when the users have multiple stocks and need different types of updates, like email, SMS notifications, or push alerts? So let's see how quickly this becomes messy. So here's how the code might look when we try to add email and SMS alerts. So this is our stock class. The dashboard class remains the same, but we added the email and the SMS alerts class, which simply takes the stock. And this is for the simplicity. Here, the actual implementation would be like sending an actual email or sending an actual SMS. But for the simplicity, we are just like printing out the stuff. So here we define the Apple stock. We define the dashboard, we define the email alerts for that stock, we define the SMS alert for that stock, and every time the price is updated for the stock, like from 150 to 160, we have to call the update or send notification method for those classes. So you got an idea, right? This is only for the one stock. What if we create an Amazon stock? So we'll have to again create instances of the dashboard, email, and SMS classes, and again call like update method manually for that Amazon stock as well. So surely this approach quickly becomes unmanageable. So you have to manually link each stocks to its notification. And when you add more stocks or more notification types, your code grows exponentially. Bugs become harder to trace and scalability is completely gone. So here's where the observer pattern saves the day. Let's see how. Thinking of an observer pattern is very intuitive. To give you an analogy, imagine there's your favorite YouTube channel and you want to keep track of the latest videos that channel posts. So what do? You push that subscribe button and hit that bell icon. So you are an observer because you want to keep observing for the new update or the new video. So what you do, you as an observer subscribe to that YouTube channel, what we call it as a subject. So in the observer design pattern, there are two key players. The one is the observer and the other is the subject, and they are linked together through a subscription. So observers subscribe for updates from the subject. One thing to notice that whenever you subscribe to a YouTube channel, there are many people like you who also subscribe to the same channel, right? So it doesn't matter for the YouTube channel who all people have subscribed to it and are observing or waiting for the new video. All the subject cares is about pushing up the updates or just posting a new video. And it's the job of the observer now to consume that update in any way they want. So we have an observer, like in our example, it can be the SMS alerts or the email alerts or the dashboard. These, what we call them as observer, because they want to keep track of the new price updates for a given stock. And the stock price is what we call a subject. So let's simplify our code with the observer design pattern. So let's modify our class to implement the observer design pattern. So in our stock, apart from the name and price, we also have observers in our stock class to keep track of all the observers who are observing this stock price. So the one thing is that, and the second thing is let's have the add and remove method for the observer. So that would be like self dot observers dot append and observer. Similarly, we have remove observer. That would be like self dot observers dot remove and observer. Okay. So now we have a list of observers observing our stock prices, we also need to have the notify observer method to notify all the observers whenever there's a price change or maybe some other event occurs. So notify observer. And so this is one of the most critical step in implementing the observer design pattern. So what this tells us is if we want to have like centralized control of notifying to different observers, they need to follow a same interface. So the same interface is like they should simply have the update method that accept this stock as an input. So if we follow the same interface for all the observers, our life becomes very easy by just calling this notify observer method every time the stock price is updated. So in the set price, we will also call notify observer, and that's it. So with this, our observer classes will be pretty neat in their implementation. So we don't need to have stock while initiating the dashboard class. All we need to have is the update method that should take the stock as an input. And we can safely remove the init call. Awesome. And same goes for the email alerts. And this will be stock.price, stock.name, and stock.name. So how this will change the actual main code. So let's see an example. Let's remove this and we have the Apple stock. Let's also have, for example, Tesla stock. TSLA. I'm not sure, maybe 400. Okay. And let's have our observers in place. So we want dashboards, we want email alerts, we want SMS alerts. Now, what we can do is we can independently add observers to stocks. So, for one stock, maybe we can add all the observers like dashboard, then we can add email alerts, and again, we can add SMS alerts as well. But for the Tesla stock, we only choose to have dashboards and email alerts and not SMS alerts. So, dashboard, and that's it. So that's all we have to do now. Now we don't need to manually call the update method for each observers. All we have to do is every time the stock prices change, say for example, we set the new price for Apple, say 150, and say Tesla, maybe 500. That's it. Let's try to run it and see what we get. Oops, no attribute update. My bad. I told you, all the observer needs to follow the same interface update. We should have update. I was being a little silly, but let's define um, the observer class. I should have, um, okay, awesome. So we have the observer and update method. So let's have our observers actually implement or extend the observer class. That's why by following object-oriented programming, you tend to make less error. So now should be update and update. Awesome. So you see, dashboard has been updated with 150. Email has been sent for the Apple stock for 150, and SMS is also triggered for the Apple stock. Now, since we only had dashboard and email alerts for the Tesla stock, we see those two have been triggered. Now let's again update the Apple stock price to 155 and see what happens. So first we see 150, 150, 150, then we get the Tesla notifications, and then again all the dashboard, email, and SMS are updated with the new stock price. And that's how we do that in code. So now anytime a stock price changes, all its observers are automatically notified. This design is flexible, clean, and scalable. So let's break down the pros and cons of the observer design pattern. Let's start with the pros. The first one is the scalability. So now with this new code, we can easily add or remove observers without changing the stock class, right? We don't have to touch the stock class again. All we have to do is, if we no longer want to have email notifications for Apple stock, what we can do is apple stock dot remove observer and just say email alerts, and that's it. It's done. No need to touch the stock class again. The second is the decoupled code. Observers and subjects are independent, making the code easier to maintain. So now we have seen that observers are pretty independent of the stock class. They do call some properties, but again, this can be more simplified with the getter and setter. So there is always scope for decoupling. Now the third one is the flexibility. We have only created the observer once, and we have seen that the same observers have been used for multiple stocks. Like we have used the same dashboard observer for the Apple stock as well as Tesla stock. So that gives us a pretty good flexibility on using different components as we want. Now let's look at the cons. I won't say it's a con, but it's like managing large number of observers can add complexity. It's not actually a con for observer design pattern, but if you have to add like lots and lots of observers, then definitely there is something wrong. Just don't try to implement observer design pattern at all the places. That's not a good idea. So it's not actually a con, but a con. So let's talk about the real life use cases of the observer design pattern. The typical example would be the stock market apps. Just like our example, if you want it for real-time price updates, we can have the observer design pattern. The second one is the e-commerce app, where they notify users when a product price drops or restocking happens. The third one is the chat applications, like sending notifications for new messages or group updates. So the last but not the least is the UI frameworks. So for example, React state management works on a similar principle. Whenever there's a update in the state, it notifies the other components who are listening to it. Or if you have used RxJS while building web applications, or in general in JavaScript, whenever we use reactive programming or like RxJS, we have the subscriber observers thing in place. So that's actually an observer design pattern. So that was the observer design pattern in action, turning a chaotic notification system into an elegant, scalable design. So if you found this helpful, try and recognize where you can use this code or where you can use this observer design pattern while building your projects. And remember, great code isn't just written, it's design. Imagine you're building your dream house. You want a spacious living room, a modular kitchen, three bedrooms, and a backyard garden. But what if someone offers you a pre built home without any customizations? You feel stuck, right? That's the same challenge developers face when creating objects in software that requires different configuration. Enter the builder design pattern, which simplifies the process of creating complex, customizable objects step by step. In this video, we will learn how to use builder pattern, walk through an example in Python, and explore its real-world application. So let's start with a basic scenario where we want to create a customizable house with predefined attributes like rooms, bathrooms, and features. Here's a basic implementation without using the builder pattern. So this is how our house class looks like. This is our constructor, which accepts different arguments like number of bedrooms, bathroom, and if house has the kitchen, garden area, and a garage. We have a string method that just split out the features of the house, like the number of bedrooms, bathrooms, and like the other details. And this is how we create our new house. So in the constructor itself, we pass in the different parameters. Here we have three bedrooms, two bathrooms. We have the kitchen area, we have the garden area, but we do not have the garage since the last argument is false. And that's it. So this simple implementation works for basic homes. But as customer demands more options like swimming pool, gym, or extra floors, managing this configuration in a constructor becomes a nightmare. Let's see why. Imagine we now need to include configurations for solar panels, smart home features, or specific room sizes. Now, this is what our constructor might look like. We might need to add arguments for pool and solar panel, and maybe if we want to have a smart home or not. So let's change our constructor. So this constructor is bloated, hard to maintain, and confusing to use, right? Worse, if you forget to set one parameter, the whole object could break. So now if you want to use the new constructor for creating a new house, we need to add three more parameters. Like, do you want a pool? Let's say true. How about solar panels? Let's say false. And what about the smartphone? Let's again say false. So you see, it's not very readable. Clearly, we need a better way to create our dream home. And this is where the builder patterns comes in. The builder pattern lets us create complex objects step by step in a flexible and readable way. Let's refactor our home building example using this pattern. So let's just also add the pool, solar panel, and smart home. Awesome. So let's try to run this code. So here we see we get our home printed like this. Awesome. So let's refactor our home building example using the builder pattern. So let's keep our house class as it is. Here now we create the new class called house builder class. Okay. And let's define this init method where we have some initial values for the bedrooms, bathrooms, same for the kitchen. I mean, let's let's initialize with some initial value. So garden maybe false, garage again maybe false. Everything else is initialized to false except for the kitchen because kitchen is like the basic necessity of the home. So this is the house builder class. And in the house builder class, what we can have is we can have different methods. So for example, set bedrooms. And here we can have the craft. And we can say that self dot bedroom is equals to the count and simply return self. Similarly, we can have classes for set bathrooms and again we pass in the count and we set the number of bathrooms equals to the count and we return self. Then we can have another method for the garden, add garden, which will simply set the garden equals true and return the same object. Similarly, we can have a method for add pool that will also set the pool to true and return. Then we have solar panels and smart home. So let's do it quickly. Self dot solar panels is equals to true and return self. Similarly, the last one is we have add smart home. So now we have the house builder class, which has its own constructor and different methods to independently add each feature, like how many bedrooms we want, how many bathrooms we want, if we want to have like the garden, pool, solar panels, smart home. You get it, right? Now how do we use this builder class to actually build a home? We can have like another method, a build method, which actually creates our house and returns the house objects. So it just returns house and just pass an argument to it. So the first would be the bedrooms, then the bathrooms, then the kitchen, then the garden, then we have the garage, then we have the pool, then we have the solar panels, and last but not the least is we have the smart home. So now we have the build method which actually returns our house. So now let's see this in action. So here we will create a custom house using a builder pattern. So let's create our house builder, which is nothing but calling the house builder class. And then our custom house would be house builder, then set bedrooms. Say we want 4 bedrooms, then we want to have set bathrooms. Say we want 3, then how about a garage? Oh, I think we missed the garage part. Let's define it here. So let's add garage. Let's also add pool. Let's also add solar panels. And we'll skip the smart home. And after this, all we need to do is call the build method, right? So let's see if our custom house is created as we wanted. So let's run our code. Awesome. You see, the custom house, we have 4 bedrooms, 3 bathrooms, kitchen, garden, garage, pool, solar panels, but no smart homes because we didn't include the smart homes. Using the builder pattern, we have the process of creating custom homes clean and intuitive. Each method tree present a single step in building process, ensuring readability and flexibility. Right. So let's discuss the pros and cons of the builder pattern. Talking about the pros, the first one is the step by step construction. It's very easy to follow and highly customizable. The second is the improved readability. Each builder method is self explanatory. And the third one is the separation of concerns. What I mean by that is that keep creation logic separate from the main logic. So, talking about the cons, the first one is the boilerplate code is required. So, we require additional classes and methods. As shown in the example, we have the house builder class in addition to our house class. And second is the complexity. So it may feel like an overkill for simpler objects to build with the builder patterns. So let's talk about the real life use cases where we can actually use the builder pattern while building a software. The first one could be the real estate platform, like we saw in our example for configuring custom homes or office spaces. The second one is the game development to construct game levels or characters step by step. The third one is the travel booking apps to create customizable travel packages like flights, hotels, and if you also want to add like other activities to the package. The last one is the report generation. What I mean by that is, for example, suppose you want to assemble reports with headers, tables, and charts dynamically. So you can build the reports in stages and steps. That's the builder design pattern, a handy way to construct complex customizable objects in software. So I hope you understand now where to use the builder pattern and how it works. And I hope to see you use it in your projects. Strategy design pattern. Imagine you're shopping online. At checkout, the app offers multiple payment options like credit card, PayPal, and even cryptocurrency. Now think about how developers handle this. They could write one giant piece of code to manage all these payment methods, but what happens when a new payment method is added? The code becomes messy, it becomes hard to maintain, and prone to errors. So, what is the solution? The strategy design pattern, which simplifies how we handle multiple algorithms or behaviors dynamically. It might sound like the factory design pattern, but here we are talking about the behavior at the runtime, not the object creation. So in this video, we will explore the strategy pattern with Python, identify its advantages, and discover real-world applications. Let's start by implementing a basic e-commerce checkout system where different payment methods are handled in a single class. This is how our payment processor class would look like. It will have a process payment method which accepts method like the credit card, PayPal, or crypto, and the amount as an input. We can have like multiple if else condition depending upon which method needs to process the payment. So, for example, for the credit card, we can have all the logic for payment processing in here, and similarly for the PayPal and the other payment methods. And how do we use this? We call the processor and we call the process payment method and give it a credit card and the amount. Let's try to run. So here it is. So it says processing $100 payment using credit card and processing $200 using PayPal. So this works fine for now, but what happens if a new payment method like Apple Pay is added? We have to modify the process payment method, increasing the risk of breaking existing functionality. Now, since this is dummy method, so it looks very simple, but actually processing payment is like a huge code in itself. So the class becomes rigid and violates the open close principle. If you don't know what is open close principle, it says our code should be open to extension but close to modification. So we should not be modifying a lot of code, but we should be able to extend it. We should be able to create new classes which should work like by default with our existing code. So that's what I mean by the extension, and modification is like modifying the main logic again and again. That is not ideal. The problem with this approach is all the logic is stuffed into one method. That is the process payment method, right? So each new method requires modifying the existing code. Second, it will also require testing all payment methods again to ensure nothing breaks. This tightly couples the payment logic to the payment processor class, making it hard to extend or reuse. Now, let's solve this using the strategy design pattern. So, the strategy patterns allows us to define a family of algorithms, encapsulate them in a separate classes, and make them interchangeable. What I mean by that, let's see it in action. Here's how we can refactor our payment system. We can define a payment strategy interface which will be implemented by different payment methods into their own classes. So this payment strategy interface will have one method called pay, which will take amount as an input. So after we implement this class, for example, for the credit card payment, this is how it will look like. And similarly for the PayPal and crypto payments. So here each payment method is encapsulated in its own class, adhering to single responsibility principle. Like they will only have responsibility to handle payment done by the credit card. Or for the PayPal payment class, it will only have responsibility to handle the payment done by the PayPal. With the different classes for different payment methods, we can also have our context class, which is the payment processor class. So this payment processor class will have two methods. One is the set strategy. What I mean by strategy is if you want to change the payment strategy from credit card to PayPal, we can set that dynamically at the runtime with our set strategy method. And process payment method simply call the pay method of the given strategy. So how do we use this? So we define the processor, payment processor, and give it credit card payment as an input. And we just call processor.process payment of 100. And that's it. So the payment processor has the credit card payment strategy set to it. And when we call the process payment method, it will call the pay method of the credit card payments. So if you want to change the strategy or change the payment method from credit card to a PayPal payment, we can simply call processor dot set strategy to PayPal. And that's it. We can again call processor dot process payment. So let's try to run this. And awesome, here it is. First we call the credit card, so $100 payment using credit card. Then we change the strategy to PayPal, so it says processing $200 payment using PayPal. And then before processing $300, we again set the strategy to crypto. So here we get processing $300 payment using cryptocurrency. So let's weight the pros and cons of the strategy pattern. The first one is the extensibility. As we saw, we can now add new payment methods without modifying our existing code. So our main code remains the same. We can simply add new payment class and simply call the new strategy, and that's it. We do not have to modify our main logic. Second is the flexibility. So we now have the flexibility to switch between payment methods dynamically at runtime. And third one is the clean code. So now we have our logic divided into smaller manageable pieces. So those are all the pros. So let's talk about the cons. So there are mainly two cons. One is the overhead of managing extra classes. Like here we saw, now we have the payment strategy interface, then we have different classes for each payment method, and we also have a separate class for the payment processor. And the second one is the setup complexity. So as we saw, it requires proper planning to ensure seamless integrations. You cannot just start coding. You have to think through before writing your code to define the strategy design pattern. Let's talk about where can you apply the strategy pattern in real life. The first one, as we saw, is the payment gateway. Can handle multiple payment methods, as we saw. The second is the sorting algorithm. If we have to choose between different types of algorithm, like say bubble sort, quick sort, merge sort, we can do that based on our data size. The third one is the compression tools. So we can switch between zip, rar, or gzip dynamically. Third one is the authentication system. If you have seen on different websites which support different authentication method like username, password, OAuth, or biometrics. So that's the strategy design pattern, a powerful way to make your code flexible and maintainable. We are diving into something super practical and easy to understand, the adaptive design pattern. Trust me, this is going to make you feel like a wizard bridging gaps between mismatched systems. But first, let me paint the picture for you. Imagine this. You just bought a shiny new phone that uses a USB-C port. But wait, your charger is USB-A. They don't fit. So what do? You grab an adapter. It's a simple tool that lets the USB-A plug works perfectly with your USB-C port without needing to buy a new charger or a new phone. Convenient, right? That's exactly what the adapter pattern does in programming. It acts as a bridge between two incompatible systems so they can work together seamlessly. We'll take an everyday example, a payment system. Suppose you're building a payment system for your app. It expects a specific interface that should have a pay method. But then you're asked to integrate an older bank service class that uses a different method called make payment, like this. So as you see, there is a mismatch. Like the process payment method expects the payment interface or the payment service to have the pay method, but the bank service has the make payment method. So there is a mismatch. And if we try to run this code, this simply is a bank service and we pass the bank service to the process payment method. So if we try to run this code, this should throw an error. Bank service objects has no attribute pay. As you see, this fails because bank service doesn't have a pay method. Now you might be tempted to directly modify the bank service class to fit the new interface, right? But what if that class is a part of a third party library or legacy code base which you should not change or you cannot change? Modifying it is a bit risky, and what if other system rely on its existing interface? So here's where the adapter pattern comes to the rescue. Instead of changing the bank service, we create a new class, the adapter, that translates the old interface to match what the client code expects, right? So let's first define the interface that the client code expects. So we can define the interface and we can call it payment service, and we define the pay method as which accept amount. This needs to be implemented in the child classes. Now let's define the adapter. We simply name it bank service adapter that implements the payment service interface. So let's define the init method, and we can also have another method called pay that is a part of the payment service interface. which accept the amount as an input and simply call the bank service make payment method. And that's it. So what we have done here is we have created a wrapper around the bank service class, which simply call the make payment of the bank service class inside the pay method. So it's more of a wrapper because we want the bank service to work with our main code, client code, right? So how do we change the client code? So let's remove this. So here we can simply do bank service adapter is equals to bank service adapter, and that takes bank service as an input. So we simply give it bank service. And now we should simply be able to call the process payment and give it the bank service adapter as an input. And let's give it amount of $100. Let's try to run this code and boom, processing payment of $100 through bank service. So see how smooth that was. We wrapped the bank service inside the bank service adapter, and the client code didn't even realize the difference. We were simply able to call the process payment method onto that bank service adapter, and our legacy class was able to seamlessly work with our client code. So no changes to the original class, the bank service, so no risk. So let's try to break down the pros and cons of the adapter pattern. The first one is the reusability. We can reuse the existing classes as we just saw in the example, even if their interface doesn't match. Second is the flexibility. We can integrate third-party libraries or legacy code seamlessly. And the third one is a non-invasive. So no need to modify the existing code. So no more risk of breaking our code base. Now talking about the cons, very intuitive is the added complexity. It introduces an extra layer in our code. Second one is the overhead. So it can make simple scenarios unnecessarily complex or complicated. Now, where can we use the adapter pattern in real life? Here are a few examples. The first one is integrating APIs. So when you need to integrate third-party APIs with your application, but their interfaces doesn't match, the natural way of thinking should be creating a wrapper or adapter. The second is working with the legacy code. So as we saw, adapting to older system to work with the modern frameworks needs bridge. So that is a adapter. And the third and the very common use case is the UI components. If you're a front-end developer, you might have seen like adapting to third-party UI libraries to fit in your app's interface usually require creating a wrapper around those library classes or functions. So that's the adapter design pattern for you. So always think about the USB adapter analogy. The adapter design pattern is everywhere. That's the adapter design pattern for you. It's like a translator between two systems that don't speak the same language. Use it wisely and you will save time, effort, and avoid unnecessary headache. A pattern that's perfect for managing complex behaviors in your code. But first, let me set the stage with a relatable analogy. So imagine a vending machine. When it's idle, it waits for you to insert a coin. Once you do it, it allows you to select a snack. If the snack is out of stock, it refunds your money. The machine has multiple states. Idle, has many, dispensing snack, or out of stock. Depending on its current state, the machine behaves differently. Now imagine how messy it would be if all these rules were crammed into one single function with, lots of if else or switch statements. And that's where the state design pattern comes in. It allows us to encapsulate each state into its own class, making the code cleaner, more modular, and easier to maintain. So let's see what happens if we try to manage the vending machine's behavior without the state pattern. Let's see it in action. So this is our vending machine class. In real life, the code for the vending machine is very complex, but we have created a very simple vending machine where we have the snack count and the state of the machine, like idle, if it has money, is dispensing snack, or if it's out of stock. And similarly, we have different user action, like if inserting a coin or selecting a snack, like that. So we have the init method for our vending machine class, which has the state where we initialize it to idle because that is the most natural state of any vending machine. Then we have the snack count, which we initialize to 5. And we also have the handle method, which takes the action as an input. So if you think about it, action is the user action. If user is inserting a coin or like selecting the snack, based on the machine state, we check what is the user action, and accordingly we either change the state of the machine or we perform some action, right? So here in this case, if the state of the machine is idle and the action is insert coin, we change the state to has money, right? And here we simply print like coin inserted and you can select a snap, right? Else, if the state of the machine is idle and there is some other action from the user, so we prompt the user to insert a coin first. Similarly, if the state of the machine is has money and the user action is select a snack, like selecting snack, then we have like condition, if the machine has snack, then lower the number of snack by 1 and change the machine state to idle and just print out dispensing your snack, right? If the machine don't have snack, we simply say out of stock and we refund the amount to the user. So the other case would be if the state of the machine is out of stock, so we just prompt the user, sorry, there is no snack left. So you understand, right? This works, but as the number of states and action grows, the handle method becomes a complete nightmare. It's hard to read, test, or extend without introducing bugs. So let's refactor these with the state design panels. But before that, let's try to run our code to see if it actually works. So we first initialize the vending machine class and we call the insert coins. After inserting the coin, it should say select a snack. And then if we provide an action to select a snack, it should say dispensing you a snack. So let's see if it works. It says coin inserted. You can select a snack. Awesome. Then we have select a snack. So dispensing your snacks. Thank you. Awesome. And similarly, like the same thing again. So it works, but it's not very readable and easy to understand and definitely not scalable. So let's try to introduce our state design pattern. Let me clear the console. So the state pattern will separate the behavior of each state into its own class, right? And this makes our code more modular and easy to extend. So let's implement it. To do that, let's remove the calling code and let's first define our vending machine class. So I'll simply remove handle method for now. We'll come back to the handle method later. Now, ideally, our vending machine should have the snack count, right? And it should also have the state that we have initialized to idle. Let's also have the other states in place because now we have different classes for each state. So let's define them into the vending machine class. You'll understand why we are doing it once we also implement the code, but bear with me. So we can have the idle state. We'll simply call the idle state that we will implement in a while. Similarly, we will have the has money state, which we also implement in a while. And we can also have out of stock state. So let's call it as of now. If we have more state, we can simply add to the vending machine class. And now instead of having like a raw string, we can actually give it the state name. So like self dot idle state, right? And let's keep it at the last so it's readable when someone try to read our code. We will implement the handle method in a while, but let's first define our state classes, right? To do that, let's first define the state interface. So this is a standard way to, define interface in Python. And let's have like the abstract method. This can also be imported from the ABC. Here we define the handle method, which takes action as an input. And this will be implemented by the child classes. Okay, let's put a state interface. Now let's define our state classes. So the first one would be the idle state. So let's define idle state, which implements the state. So let's define our handle method, which takes machine as an input and the action. So this machine can simply be the vending machine and the action can simply be the string. Awesome. And we'll implement it in a while, but let's similarly first define our other states. That means of the and paste, and this can be the has money state, and this can be simply or a stock state. And let's define the handle method for each of them. So the handle method for the ideal state would look something like this. So if action equals to insert coin, then what we will simply do is we can change the machine state to has money state, and we can simply print coin inserted. You can select a snack. And if the action is something else, we can simply prompt the user to insert a coin first. Insert a coin first. And that's it. That's the ideal state class for you. Now, similarly, let's also implement the has money state. Similarly, the out of stock state. So let's implement the handle call for the has money state. So this can simply be if action equals select snack, then check for snack availability and dispense the snack, right? If there is some other action, we can simply prompt the user to first select a snack, right? So here we first check if machine dot snack is positive. That means the machine has snack. Then reduce the snack quantity by 1 and change the machine state to idle, because we have collected the money and dispensed the snack, and just print dispensing your snack. What if the machine do not have any snack? So we simply call the machine state to machine out of stock state, right? And simply prompt the user that we are out of stock and your refund initiated. Okay. So that's our has money state class. So similarly, we can also implement the out of stock state. So this can be very simple. We simply prompt the user that, sorry, no snack left. And that's it. Now, let's implement the vending machines handle call. So here, the handle call would simply be self.state.handle, right? And we pass in the vending machine, that is the self, and the action, and that's it. So see the difference. Now each state has its own class, and the vending machine class simply delegates action to the current state. Adding a new state or modifying existing behavior is very straightforward now. So let's try to run this code, define our vending machine here, and now we can simply call machine.handle insert point, and then we can call select snack. So now let's try to run this code. It says insert a coin first. That means the initial state of the vending machine is already set to idle state. Idle state, oh, there is a typo. It should be insert. Let's clear the console. And now let's try to run the code. So it says coin inserted, you can select a snack. Then it says, after we give it an action of selecting a snack, it says dispensing your snack, thank you. Now let's try to select the snack again when machine actually turns back to the idle state. And it should prompt us to first insert a coin, right? So let's run our code again. And it says coin inserted, you can select a snack. Then it says dispensing your snack, thank you. But when we try to again select a snack without inserting a coin, it prompts us to first insert a coin. So that means our code works. And you saw, right, when this code was not working in the first run, we knew that the initial state was set to idle state. So we only went here to debug our code. So it was very easy to kind of look up the code and find the error. So now it's very clear that with the state design pattern, our code is very easy to maintain, and adding a new state or modifying the existing behavior is straightforward. So let's quickly look at the benefits of using the state design pattern. The first one is the cleaner code. So with the state design pattern, each state's behavior is now encapsulated, avoiding huge if else or switch statements, as we saw in our example. Second is the extensibility. Adding or modifying states is simple and doesn't affect our existing code. Third is the separation of concern. Each state now focuses only on its own behavior. And here are a few examples where the state design pattern shines. The first one is media player. We know that when we try to play music or play a video on any media player, it has different states like play, pause, stop, etc. Second is the ATM machine. Very similar to our vending machine, ATM machine also has states like idle, card inserted, dispensing cash, etc. Third one is the e-commerce checkout. It's a little gray area, but it also has states like adding to cart, payment pending, order placed. So different states, right? So that's the state design pattern for you. It's like giving your code multiple personalities, each with its own set of rules. It makes your code clean, modular, and easy to maintain. So thanks for watching, and I'll see you in the next video.